In the previous lecture, we have already covered on the bending stress. So now we are going to proceed with the shear stress. Right? So we have a simply supported beam that is loaded at the center. It deflects or bends under load. Okay, so we are going to use the same concept, okay, as what we have used previously for the bending stress. Okay, only that now we are going to determine, okay, the shear stress for the section. Right, so as you can see here, okay, we are going to have fx, okay, on the top and also bottom of our section. Okay, so shear stress, okay, is equally important, okay, with the direct stress, okay, or normal stress, and also the bending stress in beam analysis. Right, so we are going to consider the element of the beam, okay, as shown below. Right, so with the assumptions, okay, that the shear force is uniform across the cross section considered, and the existence of the shear stress does not affect the bending, it does not affect the bending stress distribution. Right, so it will not affect the bending stress distribution. However, we are going to calculate for this new value. Okay, so as you can see here in the figure, right, so under the load, okay, we are going to have the shear stresses that is acting in this direction, okay, and the value of the stresses will be of opposite directions. Okay, so one to the top and another one is to the bottom. Right, so this is similar to what we have already considered, okay, in the shear forces in the calculation for the shear force diagram. Okay, so the equation, okay, that we are going to use, okay, for the shear stress is equals to tau equal to V times with Q divided by I times T. Right, so V is equals to the internal resultant shear force. So basically this V value can be determined from the shear force diagram. Right, then the next one is the I value, okay, which is the moment of inertia. Right, so this can be calculated, okay, based on the calculation that we have discussed earlier. Right, so the method is still the same, so this I value can be used for both bending stress and also the shear stress. Right, so it can be used to calculate the sigma, okay, as well as the tau value. Okay, then we also have the thickness, okay, which is T. So this T is considered as the width of the member, okay, member's cross-sectional area measured at the point where tau is to be determined. Right, so we need to determine, okay, the location of the shear stress first, okay, then only we can determine which value of T that we are going to use. Okay, then next is Q. Right, so this Q value can be calculated by Y bar multiply with A. Okay, whereas A prime is the top or bottom portion of the member's X sectional area, okay, defined from the section where T is measured. And Y bar, okay, is the distance of centroid of A prime, okay, measured from the neutral axis. Right, so we are going to discuss more about this later. Right, so actually, okay, we need to determine the distance, the location of the shear stress first, okay, then only we can determine the values. Okay. Okay, so shear stress in beams, right? So as what you can see here, okay, this is the application, the principal application, okay, of a rectangular cross section, okay, whereas tau maximum, okay, can be calculated using this equation of VQ divided by IT, right? So as you can see here, okay, if we are required to determine this tau maximum, okay, at a certain point, right? So as for this example, okay, tau maximum happens right in the middle, okay, which is the center of this rectangular section, right? So since it is a rectangular section, okay, that is uniform on its top and also bottom section, right? So therefore, we are going to have this section divided by 2 with the centroid that is located right in the middle of the section, right? So for this type of section, okay, we are going to have tau maximum, okay, happening right in the middle of the section, right? So the equation, okay, can be equals to 1.5 V, okay, divided by A, right? So as you can see here, the equation, okay, has already been substituted, okay, into the calculation, right? Okay, whereas we can see we have V, right? So this V is the shear force, okay, that is from the shear force diagram. Okay, then we also have H over 4, right? So this H over 4 is the Y bar value, right? So this is the Y bar value. And then we also have BH divided by 2, right? So this BH divided by 2 is the area, okay, of either the top part or bottom part of the section, right? So as for this example, this BH over 2 is actually this area, right? So this shaded area, okay, that I have shaded here in the figure is BH over 2, okay, which is the area A, okay, that we are going to consider for the calculation of the maximum shear stress, right? So we are going to consider only either one, okay, of the values. So it can be of the top part, okay, or it's the bottom part from the centroid, right? Okay. So the maximum shear stress, okay, can be calculated using this equation that has already been simplified, okay, and as for the average shear stress, okay, it can be calculated, okay, using V over A, right? So this tau maximum, okay, occurs, okay, when Q is the largest, right? So when we have the largest value of Q, and tau maximum is 50% greater than the average shear stress, right? So as you can see here, this equation that is given, okay, which is a standard equation of 1.5 V divided by A, is only applicable for a rectangular section. Okay, so for other sections, okay, such as I section and so on, right? So this equation of 1.5 V over A is no longer applicable. So you have to calculate the value one by one. Okay, so this is for a flange beam, right? So as you can see here, before I forget, right? So you can see that the shear stress distribution for a rectangular section will look like this, right? So this is the shear stress distribution, right? So shear stress, okay, distribution, okay, for a rectangular section. Okay, whereas you can see, okay, that the maximum, okay, will happen right in the middle of the section. Okay, in comparison to uh, to an I section, okay, as given in the next figure, right? So this is the I section, okay, whereas you can see, okay, that the shear stress distribution is slightly different. Okay, so you can see here, okay, that the tau maximum, okay, will happen right in the middle, okay, if the section is of a symmetrical section on its top and bottom, okay, and we can see that we are going to have different tau value, okay, for the flange section, okay, on its top and also its bottom, right? So we can see that this will be the shear stress distribution, okay, whereas we are going to have a parabolic shape, okay, on the flange section, okay, as well as on the web section, okay, with different values, right? So as for this flange beam, okay, that is shown here, okay, it is actually for a symmetrical flange beam. However, if it is not symmetrical, okay, therefore the shear stress distribution, okay, will also vary, right? So later when we go into the example, okay, then we will see, okay, that the shear stress distribution will be different. Okay, so now we look into the shear stress distribution, okay, in comparison of the rectangular section and also the I-beam section. Okay, so you can see here, okay, that on the red here is the shear stress distribution, right? So we have a parabolic shape, okay, that is for a rectangular section, okay, with zero value of shear stress on the top and also bottom of the segment. Okay, and as for the I-beam section, also we have zero values at the top and also bottom beam segment. Okay, only that here we are going to have changes in the shear stress, okay, as the size of this beam changes, okay, from the flange to the web, right? So we are going to have a new value here, okay, or a new point here, okay, and also we have another point here, okay, that is due to the changes as well, okay, and we have tau maximum happening in the middle, okay, if our section is a symmetrical I-beam, okay, and the value will revert back, okay, to a zero value at the bottom of the section, right? So we can see here that the shear stress distribution, okay, will be slightly different, okay, between rectangular section and also I-beam section. So now we will look into example 1. The beam shown in the figure is made of wood and is subjected to a resultant internal vertical shear force of V equals to 3 kN. Determine the shear stress in the beam at point P and compute the maximum shear stress in the beam. Right, so you can see here given in this figure, right? So we have a wood beam, okay, a wooden beam, okay, whereas we are given the point P. Right, so we are going to determine, okay, the value of the shear stress, okay, at point P, okay, and we are going to compute the maximum shear stress that is happening in the beam as well. Right, so based on this figure, okay, we are also given the value of V, okay, which is the shear force, okay, of V equals to 3 kilonewton. Okay, so we are going to use that in the equation. Okay, so the basic equation for the shear stress is VQ, K divided by IT, right? So that V, K, that we are going to use here, K is 3 kilonewton, K, and it has to be divided by I, K, then multiply with the thickness of that particular location, right? So we are also given, K, the dimension from the sides of the wooden beam, K, to point P, right? So for the solution, okay, what we are going to do first, okay, as for this question, since the V value has already been given, right, so you do not need to draw any shear force diagram, okay, but if it is not given, therefore you need to determine, okay, the value of the shear force at that particular location, right? So for the section properties, okay, we will start with the section properties, whereas we are going to calculate the moment of inertia, right? So the I value, okay, that we are going to use in the calculation is the moment of inertia of the cross-sectional area, right? So as for this example of a wooden beam, okay, it is of a rectangular section, right? So therefore, straightforward, we can use the equation of I, K, equals to BH cubed over 12, right? So we can just simply use this equation since it is a normal rectangular, a typical rectangular section, right? So we have here 16.28 times with 10 to the power of 6. Okay, so a horizontal section line is drawn through point P and the partial area A prime is shown shaded in the figure, right? So this is for the calculation of Q. Okay, whereas we are going to consider either one, okay, of the cross-sectional area. Okay, so it can be the top area, okay, or it can also be of the bottom area, right? So if we are using the calculation, okay, either one of these, the top A or the bottom A, right? So we are going to consider two different values of the Y bar as well, right? So we can see here, as for this example, okay, so just now we have already determined the I value. So next is for the Q value, right? So the shaded area here is this area A, right? So we can see here that we are going to consider the top part of the segment, right? So we are going to have the equation, okay, for Q, okay, is equals to Y bar multiplied with A prime, right? So therefore, A prime that we are considering here is the A that is on the top part of the segment, right? So when we are considering the area, okay, as the top part of the segment, so therefore the Y bar must also be of the top part of the segment, okay, where we are going to consider half of the distance, okay, from the centroid, right? So half of the not half of the distance is actually the centroid, okay, of the A prime value, right? So as for this A prime value, right, so we know that we have the segment, okay, that is on the top of the section, right? So therefore, okay, we are going to calculate, okay, from the center of this section, okay, to the point P, and then add this up, okay, with the distance to the centroid of the section, right? So the centroid of the section here is located right in the middle of the segment, right? So therefore, you can see here, okay, that we are going to have 50 divided by 2, okay, which is shown here, okay, and plus this, okay, with 12.5, okay, which is the distance, okay, from the centroid of the segment, okay, to point P, right? So therefore, we are going to have this, right? So this will be the y bar value, right? So we have 12.5 plus with 25 millimeters, okay. Then multiply this, so that is the y bar value. Then multiply this with the area A prime, right? So the top area, okay, or A prime value, okay, will be 50, which is the height of the top part, okay. Then multiply with the width, okay, of the top part, right? So therefore, we have 50, okay, times with 100. So that becomes the area, right? So that would be the area and that we are considering. So therefore, Q that we are considering here is 18.75 times with 10 to the power of 4 millimeter to the power of 3 or millimeter cube, right? So you can either use, okay, the Q that is from the top part, okay, or you can also calculate using the area from the bottom part, provided if you are considering the bottom part, therefore the y bar must also be from the bottom part, right? So later I'm going to show you an example, okay, whereas the calculation will be done in both directions, okay, the top and also bottom, which will actually give you the similar value of the shear stresses at the same point. Okay, right. So next, we move on to the calculation of the shear stress. Okay, we have already determined the value I, and also we have determined the value Q. Okay, so V has already been given in the question. Okay, so now we are going to consider, okay, the value T, right? So that T is the thickness, okay, at the point where we wanted to determine the shear stress. So back to the equation, right? So this is the basic equation. Okay, whereas we have tau at P is equals to VQ divided by IT, right? So 3 kilonewton meter, okay, is sorry, it's not kilonewton meter, it's 3 kilonewton is the shear force. Okay, then multiply, okay, with 18.75 times with 10 to the power of 4, okay, which is the value of Q. Okay, so this is the Q value that we have calculated using y bar multiply with A prime. Okay, then we also have the I value, okay, that we have calculated earlier, which is 16.28 times with 10 to the power of 6, and also the thickness, right? So as for this thickness or the width of the section, okay, we are going to use this value. Okay, so we know that from the figure, okay, for this P point, okay, that we wanted to determine the shear stress, okay, we have the width of the section is 100 millimeters, right? So that 100, okay, is the value that we are going to use for the T value. Right, so therefore we are going to calculate this value and we will get the final answer, okay, of the shear stress of 0.346 MPa. Right, so since tau P contributes to V, it acts downwards at P on the cross section. Consequently, a volume element of the material at this point would have shear stresses acting on it as shown in the figure. Right, so we are going to have the tau P, okay, that is acting as in this figure, right? So we have already learned about stress transformation earlier, right? Shear stress transformation. So actually, this is what we are calculating, right? So only that here we are considering, okay, the beam as a whole, right? So as for this, okay, we are going to look into part B, okay, whereas we are going to calculate, okay, for the tau maximum, okay, for this segment. Okay, so this is for the next part. Okay, so for part B, okay, answering the second question. Okay, so we have the section properties. So maximum shear stress occurs at the neutral axis. So since this is a rectangular section, therefore the maximum shear stress will happen directly in the middle of the beam, right? So since T is constant throughout the cross section, and Q is the largest for this case. So for the dark shaded area A prime, okay, we have Q equals to Y bar prime times with A prime, right? So you can see here, okay, the shaded area, okay, that we are going to consider, okay, will be this area, okay, which is the top area, okay, of the segment, okay. But if you are considering the value, the bottom area also, you are going to get the similar value, okay, because it is of a symmetrical section, okay, and it is also considering the similar values of a rectangular section, okay. Right, so we are going to calculate the Q value, okay. Then we are going to calculate the shear stress as well, right? So therefore here, okay, we are going to substitute the V, Q, and also IT, right? So when we calculate, we are going to have 0.36 MPa, and we can also use the standard equation or the typical equation that I have shown you earlier, okay, for a rectangular section, whereas we have 1.5 V over A. Okay, so this is the typical equation that is particularly for a rectangular section. If you are considering an I section or a T section, right, so therefore this equation is no longer applicable. Okay, it is only for a rectangular section, and as you can see here, if we are applying this equation, right, so we are going to get the similar answer. Okay.